So two announcements. So the first one is about Typhoon. So we will follow the official announcement for to decide how to do. And so far there's no announcement. But yeah, please prepare to receive some email if there's something. Yeah. So if there's something, I will send you an email and tell you what to do. And the second. In this case, yes, we will stay in the hotel, and then the event will be online. Yeah. But yeah, so if there's anything, I will send you an email. And second thing is about this afternoon. For those who like to join us to go to National Palace Museum, we will depart at 1:30 p.m. At Howard. So the first ground floor of Howard Hotel. Yeah, we'll go by taxi. And as usual, there's yeah. So as yesterday, there's also lunch boxes after this talk. I think it'd be too sudden. So if we do this, we should have announced like yesterday. But yeah, so this afternoon remains the same. So it will be free afternoon. Yeah. Okay.
It's my pleasure to introduce Marco Rampazzo from the University of Bologna, who will speak about simple K-equivalence and semi-orthogonal decompositions.
Yeah. So first of all, I would like to thank the organizer for inviting me here to this wonderful place and this great conference. So as the title suggests, what I'm going to talk about will be quite similar in scope to, to what Dimitri Kaledin told us today, but I will see it from a different perspective. So first of all, I will focus on a different kind of K-equivalence, so projective varieties and simple K-equivalence, which is just a subclass of birational morphisms, which are K-equivalences with some additional assumptions. And I will see this from the perspective of derived categories by means of semiorthogonal decompositions. So I will consider different semiorthogonal decompositions of the same category, and I'll try to use this in order to prove that simple K-equivalence implies derived equivalence in some cases of those kinds of objects. So I would like to start with some general information about the interaction between derived categories and birational geometry. So are you able to see my writing from back there? Or should I write bigger? That's fine. Great. So from now on, when I write dx, I will mean the bounded derived category of coherent sheaves on a variety X, which will be smooth and projective. And everything will be on C with no exception. So when we talk about derived categories and birational geometry, it's since the very birth of the topic of derived categories that people have tried to understand how much of the geometry of a variety we can recollect from this abstract gadget, which is the derived category. So how much can we say about the isomorphism class or birational class or something like that? I think one of the most exciting contributions is a theorem by Vondel and Orlov, 2003, which goes by the name of reconstruction theorem. So what does it say? It says that if X is smooth projective and its canonical bundle is ample, or its anti-canonical bundle is ample, so Fano, then we have that the fact that the derived category of X is equivalent to the derived category of another variety Y implies that X is isomorphic to Y. So this is very nice because it says that the derived category in this specific case, ample or anti-ample canonical bundle, reconstructs the isomorphism class of the variety. So it's a very interesting invariant. And well, this is very nice, but the problem is that if you steer out of this case, you end up finding counterexamples. So, I mean, what people tried to do was to try to see whether it's possible to relax the assumptions and try to find a way to describe the derived category as, for instance, a birational invariant. So can we say something like that? Well, of course, this doesn't hold for all varieties. We have, for instance, some counterexamples among Calabi-Yau varieties. I can say something about that. So one famous counterexample is by Ottem and Rennemo. And okay, 17. And independently, same counterexample by Borisov, Calderaro, and Perry. So what they did was to consider the intersection of two different images of the Grassmannian G25 inside the Plucker space P9. And for a general choice of this intersection, you get a smooth Calabi-Yau threefold. Okay. And you can construct pairs of those varieties such that they are not birationally equivalent, but they are derived equivalent. So derived equivalent, but not birational. This doesn't work in this case. And a similar example has been constructed by Manivel, same year. So what he did was to consider the similar setting, but with but substituting the Grassmannian G25 in its Plucker embedding with the connected component of the orthogonal Grassmannian or G510 inside its spinor embedding P15. The construction is quite similar, and you get a counterexample among Calabi-Yau fivefolds. Okay, so what can we do at this point? Well, the thing we can do, and the thing that has been done, was to consider a specific kind of birational maps and try to understand whether in that specific case you can find that those birational maps preserves the derived category. So the maps I am talking about are the K-equivalences. So one defines K-equivalence. So I will give a different definition among smooth and projective varieties, so slightly different. So we take X and Y smooth projective. So we say that a birational map from X to Y is a K-equivalence if one has something like this. You have X, Y, you have a variety Z with maps G and H such that G pullback of the canonical divisor of X is linearly equivalent to H pullback of the canonical divisor of Y. Okay, so this is a K-equivalence. And why is there this conjecture, which is due to Bondal, Orlov, and Kawamata, about the fact that this should preserve the derived category? So let me write here the conjecture. (2002) X, Y, K equivalence implies dx dy. So why is this supposed to be true? Why do people believe that this should be actually the case? Well, because this can be seen as somewhat a generalization of cases which are known to work since before. And I'm talking about standard flops and Mukai flops. So in those cases, this is known to be true. So let me give a couple of words about that. Here. Yes. I'm sorry. Oh, yeah, of course. Okay. So yeah, like this should be okay. So what is a standard flop? You have like a birational map x to y, which is resolved by a variety z, which is the blow up of projective space on both sides, the exceptional divisor here being the product of such projective spaces. And you can do the same thing in families somewhat. So what you do is you can replace the projective spaces with projectivizations of vector bundles. Okay. So here above, you will have your Z, and inside the exceptional divisor will be a fibration of PR cross PR with some R. I mean, the rank of those bundles is R+1, of course. And those guys maps to a base B. Okay, so this preserves the derived equivalence, as I said, by a theorem of Mondal and Orlov, 95, back to 95. And well, the other famous example that works is Mukai flops. So the situation here is quite similar. What is the difference? It is the exceptional divisor. And the way, of course, that this guy is embedded here. So here we have like x, y, er, er, z, and the exceptional divisor will be a hyperplane section inside this guy. In other words, it will be a flag variety 1 r r+1. Okay, I should say that it is Mukai flop. And what about the version in families? You have that instead of the projective space, again, you take the projectivization of a vector bundle over a base B. And instead of this flag, 1 r r+1, you get a flag bundle, 1 r and some bundle, which is the same bundle here. Okay. So it's a locally trivial fibration with fibers isomorphic to this guy. It's okay. Let's use a different notation. Okay, flag bundle. Good. So this works. This works in particular by Kawamata, 2002, and Namikawa, 2003. So this is nice, but the problem is that so far it's quite a hard problem to try to generalize what we know from this to the general case of K-equivalences, because K-equivalences can be much wilder than this. So what can we do? What we generally do, we try to find a subclass of birational maps which still generalize those guys here, but they are way simpler than the full-blown K-equivalence, right? So I'm talking about what is called simple K-equivalence, and I'm going to define it now. Okay, so the definition is due to Duoli 2017. And it is the following. So consider a K-equivalence as we've been defining above, okay? Let's give it a name. Now it's mu. So we say that mu is simple if, well, this is G and this is H as above. So if G and H are blow-ups in smooth centers. Okay. Now connected. I would say connected. So thanks. Yeah. Thanks. So in smooth connected centers, and what he proves as well is the following. Same paper. In the setting above, H and G have the same exceptional divisor. Let's call it E. And well, that's not so surprising since we want to generalize this, right? We have the same exceptional divisor. So what we want to do is really to generalize this kind of thing. Okay. So in the case of standard flops, this common exceptional divisor will be a fibration of PR cross PRs, while in the case of an Mukai flop, we will have a fibration of flags or flag bundle. So yeah, it is. The proof is 2 lines. Actually, what you do is to compute in 2 ways the canonical bundle of this guy. You find out that, I mean, the 2 guys have the same class, but they're exceptional, so you can move them around. That's the case. Yeah, precisely. So this gets really nice if you consider the following fact, which I will probably have to write there. Okay. So this is a theorem by Kanemitsu, 2017. No, just this. Well, this is actually a lemma in the paper. It says that in the setting above of simple K equivalences, the 2 blow-ups have the same exceptional divisor. It's just this. Yeah, well, it's a lemma, but still, I mean. Yeah. Okay. Okay, so what this theorem says is the following. So if we have a simple K equivalence as above, then we have the following kind of diagram. So maybe a pen would be nice. Of course, we have this. We have mu. Then we have the centers. The exceptional divisor here. And we have 2 maps here. So let me call P and Q those 2 maps, and alpha and beta those 2 maps here. So we have that B smooth projective. Alpha and beta are extremal contractions. Then we have that the outer square commutes. So this. And then we have that the vibration from E to B, which you can call alpha composed with B or beta composed with Q since it's commutative. So let me just call it E to B, is a locally trivial vibration of roofs. So whatever roofs are, and I will define them in a while, actually, this theorem says that if you have a simple K-equivalence, then it is exactly like a standard flop or a Mukai flop, but with the difference that this vibration from E to the base B is allowed to have different fibers. Still locally trivial, but it's allowed to have fibers which are more general Fano varieties of Picard rank 2, which are called roofs. So what are those roofs? No, not necessarily. They can be Grassmann bundles, for instance. Yeah. You might have, for example, you might have that this guy is a Grassmann bundle, G25. I mean, you have a rank 5 vector bundle. So you have a G25 bundle over here. You have a G35 bundle over here. They're isomorphic. And here above, you have an F235 flag bundle. You can have that. If you choose a point here, any point here, you get that this guy is G25, this guy is G35, and this over that point, of course, is F235. They have two projective bundle structures. So you can get something like this. I'm going to get to that in a minute. Thanks. Yeah, I have to erase. So I stated the theorem of Kanimitsu without telling you what is a roof. So I think it's time to say it. So instead of writing the definition of roofs, I will write a characterization, which is still in the same paper by Kanimitsu. Yes, yes. The theorem says that if you start with a simple K-equivalence, so you already have this, this, and this for free, then you have that. You have those maps, the outer square commutes, and this is a vibration of roofs. This is the idea. Thanks. Characterization. Okay. A roof of projective bundles, let's say PR-1 bundles, is a smooth Fano variety of Picard rank 2 and index R. Okay, such that its extremal contraction are projectivizations of vector bundles of the same rank R. So R is the same R you have here and here. Okay, so this is a roof. Let's give some examples of them. I will give lots of examples for a specific reason that will be clear in a minute. So can I write here? Do you see? Because I would like to keep this on the board for a while. Can everyone see this? Perfect. So well, first of all, we have two of them for free, right? Pn plus Pn. And we have F1 n minus 1 n. So this is related to the standard flop, as I said several times, and this is related to the Mukai flop. Okay, now what I was discussing with Evgeny a minute ago, this case, F n plus 1 to n plus 1. Okay, so if you look at this variety, at this flag variety, you see that it is a homogeneous variety of Picard rank 2, so it has two projections to Grassmannians, which are Gn to n plus 1 and Gn plus 1 to n plus 1, which are isomorphic. And you can see in several ways that this guy is a projectivization of the dual tautological bundle on the Grassmannian n plus 1 to n plus 1, and simultaneously the projectivization of the quotient bundle of Gn to n plus 1. So two projective monostructures, you can compute its canonical class, and yeah, you get that it fits in this description. Okay, so do we have a flop associated with this? Yes, it's sometimes called the Grassmannian flop. Then we have another example, another series of examples in the realm of symplectic Grassmannian, symplectic flags, actually. So IF n minus 1 and 3 n minus 2. Okay, so if you look at this and you play a bit around with representation theory, you get that this maps on a projective space and on a Lagrangian Grassmannian, if I'm not mistaken. And those two maps are projectivizations of vector bundles. So this is as well related to a known construction, which is the so-called Abwaf-Seagal flop, which has been studied by Seagal, who attributed it to Roland Abwaf. So I have to say that this construction in the paper by Seagal is local. So what he does is a bit different from this. So he considers, instead of considering projective varieties, birational with this kind of construction, he considers total spaces of vector bundles over homogeneous varieties. So it's kind of a local construction, but still it's somewhat similar. And the structure is more or less that one. But the way he proves the derived equivalence is totally different. Then we have OG n minus 1 to n. So this is a this is an orthogonal flag, actually, because it Picard rank 2, which maps to orthogonal Grassmannians. And then we have the more exotic cases. So well, this, I don't think this has a name, so I don't think anyone studied this and proved derived equivalence. While in the case of G2 over B, this is called the Weda flop, studied by Weda, of course, still in a local setting. And the most scary of all, F4 quotiented by a parabolic subgroup, which for those of you who like homogeneous varieties, is given by the choice of the second and the third simple roots, actually. So this maps to two F4 Grassmannians, and but it's quite a complicated construction, and I don't think there's any result about that so far. So why did I bore you with all this? Actually, because those examples are all possible roots which are homogeneous. All possible rational homogeneous roots. And this is proven by Kanemitsu. Okay. So actually, you study this systematically from a point of view of representation theory. You start from a rational homogeneous variety of Picard rank 2. And since it is a rational homogeneous variety, you understand what are the maps, the external contraction it might have. And case by case, you find out that you can't go out of this list, actually. So why am I saying this? Because, everyone can think, well, why do we focus only on the homogeneous case? There might be lots of stuff among non-homogeneous varieties, which has two projective monostructures and all this. So far, there's only one example, which doesn't fit in this list. Yes.
Can anybody hear me?
Yes.
Just I'm on Zoom, and just so you know, the camera doesn't move.
I see. I
cannot
see.
see anything on that you wrote on the
This is
other board.
important. So can we? Is there a camera around here, or it's? Oh no, it's over there. Okay. Okay. Yeah. Yeah. So this list, I can tell you what it is. Or no, well, no, that's not fair. That's not fair. I can write it very, very quickly here. Sorry for that. I didn't consider that. And you can also find it on a preprint of mine, and even before on the paper of Kanemitsu. There's the list as well.
I already have that paper. I just want to stop you from keep using
sorry?
that board. I just want to stop you from
Okay.
keep using that board.
Great. The organizer told me that they can take a picture and send it. So I think this might solve the problem. Thanks. Sorry for that. So, okay. So since we have this nice list of homogeneous roofs and only one known non-homogeneous roof, this is still open, by the way. We don't know if there's other of them. Still, I mean, it makes sense to focus on the case of homogeneous roofs and to define something like homogeneous simple K-equivalence. That's. Oh yeah, of course, I can tell you something about that. Yeah, I just have this space here. So what do? You take a quadric of dimension 5. Okay, so over this guy, you have the spinor bundle. Let's take its dual. This is a rank 4 globally generated vector bundle with a space, 8-dimensional space of sections. If you take a general section of this guy, so this is top chunk plus 0. So if you take a general section of this guy, it defines an embedding of O inside this. So let's call small s this guy. So if you take the quotient of this map, you get a rank 3 vector bundle, which is called an Ottaviani bundle. You have a 7-dimensional moduli space of those guys. So what you do is just to take the projectivization of this over Q5 and consider the other external contraction. That's nothing but another map to Q5. So how do you do that? You can see Q5 not just as a G2 over B1, over P1 variety, but you can see it also as a B3 homogeneous variety. So actually this embeds in the flag B3 quotiented by P13. So that guy of that kind of thing, which maps to P6. Then you take a hyperplane section, you base change, and you get that. So it's a construction like this, actually. So still rooted in homogeneous geometry, but this guy is not a rational homogeneous variety. So it qualifies as a not homogeneous roof. I tried to find other possible examples like this, but I didn't come up with anything interesting. I'm sorry? Yeah, almost homogeneous. Yeah, I could say that. I think so. I think we might say it like that. Yeah, I think so. I think so. Which is also something that happens here, actually. No, not exactly, because it's not a roof. The other example I had in mind is asymmetric, so it's not that the case. But this, back to this, I think, yes, it might be. Yeah, it's a hypersurface. Yeah, of course, of course. You take a projectivization of a rank 3 guy instead the projectivization of a rank 4 guy. So yeah, definitely. And with respect to this map here, okay. So yeah, that's the case. Okay, so let me say something about homogeneous simple K-equivalences. So I will leave this diagram here because we will often refer to it if I don't break everything. Okay. So at this point, since we have this list and it is completely exhaustive in terms of homogeneous roofs, we can naturally define homogeneous simple K-equivalence. Okay, but I will define it. I mean, I won't just say we take a simple K-equivalence such that the exceptional divisor is a fibration where every fiber is isomorphic to one of those. I will define it in a slightly different way, which is more comfortable for computations in terms of derived category. So I will say this. So we take G over P, a roof, of course, homogeneous, and this V over B, a principal G bundle. With B, smooth projective. Okay, so a map, a birational map, move like this as above, so as here, is a homogeneous simple K-equivalence if the exceptional divisor is this, V times G over P, where this product is a balanced product, which is the quotient with respect to the diagonal action of G on the two factors, okay? So why am I defining it like this? Because I don't want just a fibration. I want something like a flag bundle, right? So if you have a flag variety, you have a flag bundle, which you define exactly like this, where G is a group of type AN. If you take an orthogonal Grassmannian or a symplectic Grassmannian, you can do exactly the same. You get an orthogonal or symplectic flag. And this construction holds also for the other more exotic cases, actually. So it's just a matter of describing. Mm-hmm.
Are alpha and beta local or they semi-power type?
Yeah, indeed. No, they're locally trivialized. Safe. Yeah, they're locally trivial because let me think. Why are they locally trivial? I'm sure they are, but I'm trying to think why. Do you think? Yes. Yeah, but you might have that the fibers here are equidimensional, but then here they jump over something. I don't know. I have to think about it, and then I'll get back to this. Thanks. So, so we define homogeneous simple K-equivalence in this way, and it has a nice property, which is the fact that if you define it like this, let me go maybe above. Okay. If we define it like this, we have that we can extend homogeneous vector bundles and exact sequences from the fiber to the whole exceptional divisor. So the idea is that if you have like the category of equivariant vector bundles over G over P, you have a functor to the category of representations of P. And this this functor is just restriction. You can go back by taking this construction. So this restriction, you can go back by taking G cross P empty space. And in the same way, you can go to vector bundles over the full exceptional divisor. And this functor here is this. Okay, so it's like what happens on a flag bundle, right? Or let's say a Grassmann bundle. You have a Grassmann bundle, GKE, where E is a rank n vector bundle. This flag bundles comes with a tautological and a quotient vector bundles, which are bundles that restrict on every fiber to the tautological and quotient on a Grassmannian. And this happens for every Schur power of those guys. And so eventually for every homogeneous vector bundle on the Grassmannian, you can extend it like this. So, okay. And well, this is more or less the geometric construction I had in mind. Now, in the last 20 minutes, I can say something about semiorthogonal decompositions. So let me go here. Yes. So I'll quickly describe a bit hands waving what a semiorthogonal decomposition is. And then I will say something about the main tools we're going to use to apply the study of semiorthogonal decompositions to simple K-equivalence. Okay, so a semiorthogonal decomposition let's abbreviate it with SOD as usual. For the derived category of a smooth projective variety X, of course, this holds in general for triangulated categories, but I want to, I want to be lazy since we are working with derived categories of smooth projective varieties. I will just say this without any other assumptions. Okay, is a collection A1 up to AN of admissible subcategories such that, well, first of all, there are no X towards the left, which means more precisely that for every object E in AI and F in AJ, one has X E F equal to 0 for J bigger than I. So if like F lives here or E lives here and F lives here, there are no maps from here to here, and I'm taking the full X, so in every degree. So I should write this. Okay, better. J smaller I. And then we have that the X must be the smallest categories. The smallest category, sorry. Containing all the AIs. Okay. So the general way to write this thing is with angular brackets. A1 up to AN. So this is the way people generally write semiorthogonal decomposition. So a special nice case is full exceptional collection. So what is it? It is a semiorthogonal decomposition where all the subcategories you have here are generated by a single object. Okay, and you also ask some cohomological condition on those objects, which is the fact that the self X of each of them must be isomorphic to C in degree 0 and 0 everywhere else. So you also ask that X EI equal to C in 0 and 0 everywhere else. This is the XP. Okay. So this is very briefly a semiorthogonal decomposition. And how can we work with semiorthogonal decompositions in this setting? Well, we can use a very famous result in this field, which is again due to Orlov, and it is known as the blow-up formula. So as the name suggests, we are going to compute semiorthogonal decompositions of blow-ups. Okay, so we have the following. This is from 96. So we have that it's C and X are smooth projected. What happens with C inside X codimension R? Then we consider the blow up, right? We have C inside X. Here we have the blow up in C of X and the exceptional divisor here. Let's give names to the maps. This is I, this is pi, and this is pi bar. Okay. Then we have a nice semiorthogonal decomposition of this, which is semiorthogonal decomposition of the blow up of X in L, in C, sorry, is given by this. You take the push forward of pi bar pullback of the category of C. So the category of C, you put it back here and push it forward here. But before pushing it forward, you twist it by the Grothendieck line bundle minus R plus 1. Okay. So you have this. Then you do this for all possible twists up to the following. Minus 1. Okay. And then you have the pullback with respect to pi of the category of X. So this is a bit messy, but what it means is that you have several twists of the category of this, pulled back here, and then pushed forward here. So you twist by the relative O1 of this projective bundle, E over C, and then at the end you have the pullback of the category of the base. Okay. So you know where I'm going because those are two blow-ups. So of course, I'm going to write the derived category of this in terms of this and this, and simultaneously in terms of this and this. So I'm going to compare them later. But before doing that, there's another thing I should say, which is the fact that the category of those guys can be written in a simple way. They have as well semiorthogonal decompositions, and those semiorthogonal decomposition can be deduced by a theorem due to Samokin. Which is a generalization of a result by Orlov, 93. Okay. So Orlov did it for Grassmann bundles, Samokin for flat proper fibrations, so flat proper morphisms. So, okay. I already read it. So we have that B and X as smooth projective. Then we take flat and proper morphism X to B, and this very restrictive hypothesis, we need to have a sequence of objects, E1, En, in the derived category of X, such that on every fiber of this map, they restrict to a full exceptional collection. So the derived category of a fiber over point B has a full exceptional collection, E1 restricted to the fiber, up to En restricted to the fiber. Okay, so I hope it's understandable. I'm just taking this collection of objects and I'm restricting it to a fiber for every point here, for every B in B. Then we have that if this is true, we have a semiorthogonal decomposition. That's the following. So the derived category of the vibration will be equal to the derived category pullback of the base twisted by this object E1, and then the same thing for all the other objects. Okay. So actually, we can globalize semiorthogonal decompositions on a fiber to the whole vibration. So what we can do is to take the formula by Orlov and write two semiorthogonal decompositions of Z, one containing some copies of the category of C and a pullback of the category of X. The other one in this way. Then what we do is to plug in this result here in order to write the derived category of C1 as several copies of the pullback of the category of B twisted by a full exceptional collection of the fiber. So there's something I have to say here.
Sorry, so in the theorem you write down, so pi is only supposed to be flat, and for singular fiber, what is D? Yeah, pi minus.
That's a problem. I mean, this general result by Samokin holds for flat proper fibrations as long as you are able to find a full exceptional collection for every fiber. Of course, if there are singular fibers, it's a problem.
Implied that not smooth because all the fibers will be smooth and smooth.
Yeah, I think so. I think that's a good point. Anyway, we are interested in smooth fibers, locally trivial fibrations, so we are really safe. So this is a more general result. I wanted to quote it like this, but what we actually need is just something for local integral fibrations of Riemannians. Okay. So so now we have to take a nasty assumption. We want to assume that the fibers of alpha and beta have a full exceptional collection of homogeneous vector bundles. Well, this looks like a very big stretch, but actually it's a solid conjecture, and it is known to be true for most of the cases you see on this board. And yeah, it's an open conjecture since probably 10, 20 years for many cases. Like, for instance, this guy is particularly hard to understand from that point of view. But still, I mean, here, and here, and I think also here, you have full exceptional collections for the fibers of both those maps. Yes. Yeah, I'm sorry. I am assuming that the roof is homogeneous, since when I defined it, I'm assuming I'm working in that case. Yes. So if you assume this, what you can do is to use the result by Samokin and finding that those objects actually exist. Why? Simply because you have homogeneous vector bundles which form a full exceptional collection on every fiber. Then you use the fact that you can extend them to the generalized Grassmann bundles, and you get exactly the objects seen in here. So at the end of the day, you find two semi-orthogonal decompositions for Z here, which are the following. I mean, I write them in general. They have the following form. You will have B. Let me write that B is the pullback with respect to P and alpha, or equivalently beta and Q of the derived category of B. Just as a shorthand notation, I use this fancy B for meaning this. Tensor some object F1 to B, tensor some object Fm, and then what is this map G? Pull back the X. And similarly, from the other side of the diagram, you have B tensor, let's say F tilde 1 up to B tensor, say F tilde M, H pullback of dy. So I'm writing this to mean that we have two semi-orthogonal decompositions where the semi-orthogonal complements of the pullbacks of the categories of those two objects are given by blocks, which are pullbacks of the category of B to the exceptional divisor, tensored by objects which are extensions of homogeneous vector bundles to the generalized Grassmann bundles you have here. And of course, then you have to push forward them with respect to this embedding, but I didn't write it here to unclutter the notation somewhat. So I can state now the main theorem, and I can give very few words to describe how to prove it from here, because I'm a bit out of time. So let X to Y be a homogeneous simple K-equivalence with exceptional divisor E over B with fiber G mod P, where G mod P is of the following types. We have the already known cases, Pn cross Pn, F1 n plus 1. But then we also have F2, 3, 5. You have G2 over B, and you have IF 1, 2, 4. Okay. Then X to Y satisfies the decay conjecture. So we add to the cases already known by Bandalorlov, Namikawa, and Kawamata here, we add one of those, we add one of those, and we add this one. So all the simple K-equivalent homogeneous maps of those types, while still we have some other to prove. So how do we prove this? How do we prove this? The idea is that we start from those collections, we start from those decompositions, and then we want to apply mutations of semiorthogonal decompositions. So what is a mutation? What is a mutation? A mutation consists in taking a semiorthogonal decomposition and exchanging the blocks, transforming one of them into something different. So the idea is that you project it to the semiorthogonal complement of the other block. So if you have something like this, A, B, then you can write this as B here and something else here, which is generally called RBA. This is particularly simple, and also you have left mutations defined in a similar way. So instead of giving the general definition, I can tell you that this is particularly simple if instead of having just admissible subcategories, you have an exceptional collection. So categories generated by a single object. You have that the left mutation of an object E, of an object F, sorry, through E can be written as the cone over a map from E tensor X E F to F, okay? And similarly for the right mutation, so for E F objects. So the idea is that we can try to reconduce to this simpler situation. What we do is to prove that in our cases, the mutations commute with the tensor product by this pullback category. So we can do that by some technical homological computation. And then we are left with mutations of objects which are described by globalizing to, those Grassmann bundles, some homogeneous vector bundles on Grassmannian. So objects defined by representations. And in that case, the same pattern of mutation is what appears in similar problems which are based on trying to understand derived equivalence of Calabi-Yau varieties described by Roof. So that's a apparently totally detached problem, which is the following. If you take a homogeneous roof, let's keep it homogeneous, like this, then you take a 1-1 section here. If you push forward this section here and here, you have two smooth Calabi-Yau varieties of the same dimension. If you write the semiorthogonal decomposition of this 1-1 section, you get the categories of the Calabi-Yaus, and you get objects which are described by the same representations that describe the objects here. So with some work of homological computation, you can say that if you have a sequence of mutations that works here, then you can extend them here. And that's exactly what we have. That's exactly what we have. So in the case of G2 over B, the mutations are due to Kuznetsov. Then the case IF 1, 2, 4, it's Morimura, 19, while in the case F 2, 3, 5, the mutations are due to Kapuska and myself. 2017. Okay, so if you're able to find the mutations here, which is a way simpler problem, Then you can extend them to this case, and you can prove that the associated class of homogeneous simple K-equivalences satisfies the decay conjecture. And I think I should stop here. Thanks a lot for your attention.
Like,
Of course.
in general, for this simple K-equivalence, we expect C1 to be birational.
In general,
They are stable birational.
yeah.
In your case, they are birational because the bundles over G local trivial bundles.
Yes, yes.
In general, we
Mhm.
expect them to be birational.
I don't know. I don't know. Because, I mean, because there are many more instructions that prevent me to think about the general case starting from the homogeneous case. So I didn't think about that actually, but I don't know. Fortunately, that's the only thing I can say.
What goes wrong in the other examples other than these?
Okay, what goes wrong is that the mutations are a mess. So, I mean, the idea is that if you think about, for instance, a Grossmannian, think about a Grossmannian, you have a GKN. For the derived category of GKN, you have n choose k objects. And those objects, as much as the Grossmannian grows, become more complicated sure functors. And if you want to compute mutations, which are not just ugly complexes, but something that you can reconduce to something coming from the other side, you need to use some geometric exact sequence generally. I mean, that's the approach I'm always using. Maybe it's not the best one, but still, I mean, I would do that. So what do you do generally? If you stay in this case, you have an exact sequence of the small tautological one, small tautological bundle inside the tautological bundle of the other Grassmannian, which has a quotient which is a line bundle. You take this and you take sure functors of this in order to find sequences that link the pullbacks of the tautological bundles from different Grassmannians and allow you to finish the task of computing mutations in that case. You have something similar for the other cases also. And the problem is that it becomes wild. It becomes a combinatorially challenging problem, I would say. So yeah, that's the abstraction.
Yeah, so,
Mhm.
so the Firefox has this local model with a contention bundle.
Yes.
here.
Mhm.
This other box has a similar local model with a bundle of.
Yes, yes. And that's quite nice because in the local models, there's another approach you can use, which is based on window categories and matrix factorization categories. So the idea is that, I mean, I'm talking about AN models. So this, and this. For the others, you have to come up with nice GIT variations, which I don't know if it's, I mean, I don't know how to do that. But at least in those cases, so all the cases for n different from 2 are still to do, so this is still interesting. You can describe a local model where you have total spaces of vector bundles, as you say. So GK, let's call n to k plus 1 just to keep it quick. GK plus 1 n, and you have the total space of a vector bundle here and the total space of a vector bundle here. So let's call this V minus and V plus. Those guys are related by a variation of GIT. And they live inside an Artin stack, which is something like a vector space consciented by GLK. And by the study of a subcategory of the derived category of this guy, which is called a window category, and some tilting bundles on those objects which stay tilting on the total spaces, then you can deduce the derived equivalence. And yeah, more or less it's this kind of computation. I think the first time it has been used is in a paper by Addington, Donovan, and Segal, something like this. Addington, Donovan, and Segal for the study of some Calabi-Yau pair of varieties. And yeah, this can be generalized to also these kind of problems, I would say. Yes. Mhm. Yeah. Hmm. I don't know. Yeah. Yeah. I don't know. I mean, if you have a simple K-equivalence, of course, it's something like this. But for more general K-equivalences, I don't know. Yes, yes, yes.
What's the connection between the two geometries? Like, so one of this, like Gauss inside those things and the other is yours. So, so the mutation in one,
Yeah.
and doing the other. Why is that?
Why is that? Because I mean, here what you do to do mutations is to use the projection. Sorry, the blow-up formula by Orlov. Here you use another different semiorthogonal decomposition, which is the so-called Cayley trick. It is actually the decomposition associated to a hyperplane section inside a projective bundle. And it has the same number of components. I mean, in the blow-up formula, you have the base and then codimension -1 times this. In the case of a 1-1 section here, and it's pushed forward here and here, what you get is exactly, if you call R the codimension is this problem, which is also, so let's say R is the fiber of the dimension of the fiber of this map. Also, it will be the dimension of the fiber of this map, actually. So you get R-1 copies of this here, and R-1 copies of the category of G over P1 inside the category of this. So you get the same structure. Of course, here you have pullbacks to this. In this case, you have pullbacks to exceptional divisors and then push forwards here, so they're not even vector bundles. But if you play around a bit with functors, you can do that, actually. So, I mean, the pattern is the same because of the dimensions of the problem, I would say, and because of the structure of the semiorthogonal decompositions of a section of a projective bundle and of a blow up. Yeah. Yes. At level of Grothendieck ring? Yeah. You can find it. Do you mean in this case, or do you mean in this case? Yeah, I think you can do that by this diagram here. So to prove that this and this have the same class in the Grothendieck ring of varieties. Oh. I don't know. That I don't know. I thought about that.
Suggest that you have a chat.
Yeah, I will think about that. Thanks a lot.
Become the same after adding the same thing, right? Right. So, but the block form of the case, I mean, this is balance, the same amount that you add.
No problem.
Take a 10-dimensional inner variety.
Yeah. Yes. Yeah, it is. It's this case for n equal to 5. It's exactly that. You get something like this. So this is the 5. So you get this if you cross out those guys. So this is OG for 10. It maps to OG 510 plus and OG 510 minus, okay? So this is a projectivization of the universal bundle of this guy. And this is a projectivization of the universal bundle of this guy. So you get this kind of situation. Problem is that I've been struggling with mutations for lots of time in this example, because I don't find any nice way to relate the exceptional collection of this and this to something here. I mean, to make them communicate somewhat. It's a bit harder problem. You have some excess sequences, but so far, no luck.
Questions? Then here again.